This video is going to cover the RSA cryptosystem. So we're going to do all the math needed to understand this pretty standard way of encrypting information on the internet. So here's the setup. Alice is trying to send a message to Bob, and Alice wants to encode the message in a way so that only Bob can open it. And so the challenge here is that if Alice and Bob don't already have a secure way of communicating, then they don't have a way to exchange any kind of secrets, it seems, in order to decide on a code in advance. Okay. But it turns out that that's not necessary. So it's actually possible for Bob to just publish what's called his public key. This is just going to be a pair of numbers. And he's going to use this public key, or at least Alice will use the public key to encode a message. So if you have a message M, you can think of it just as a number, right? So the message can be broken up into a sequence of numbers, and you just encode each number. You get a sequence of encoded numbers. So it's enough for us to be able to encode and decode a number in order to make this crypto system work. So the way Alice uses the public key to encode a message is she takes her message number, she raises it to that eth power, and reduces it mod n. Now Bob also keeps a private key, which is another number, d, but we can, just for symmetry, we'll just think of it as d also with that number n again. And decoding is symmetric to encoding. So if this encoded message is C, the ciphertext, then what we do is we take C, we raise it to the dth power, take that mod n, and that will get us back to the original message. So there's a symmetry here between encoding and decoding. And this is a basic standard public key crypto system. There are three natural questions that maybe we want to ask now if we want to be able to run this system. The first is you have to decide how to choose the keys. So we have to choose E, D, and N. We also want to know, well, why does it work? Because it's not obvious that we should be able to have numbers like E and D that can undo each other by this exponentiation. Usually you think of logarithms when you're undoing exponentiation, but it's not clear that logarithms actually even make sense in this modular arithmetic framework anyway. And the third question, which we won't really be able to answer, but we're going to look at a little bit, is why is this secure? Like, why should we feel any confidence that by encoding messages in this way that it can't be opened without that secret key? And so we have some computational reasons for why it seems to be a computationally difficult task to find D given E. And that's going to be the heart of the security, is this computational argument that any algorithm that could find D would require just some huge amount of time. So if all of this encoding and decoding is based on modular arithmetic, it makes sense for us to remember how to actually do algebra with modular arithmetic and to remember what operations are really allowed. So if A is congruent to B mod n, I'm going to leave out the mod n, but all of these are going to be mod some number n. If A is congruent to B, we know that when we use A in a sum, that we can also replace A with B in that sum, and it will get something that's congruent mod n, right? So A congruent to B means A plus 1 or A plus anything is congruent to B plus the same thing. Similarly for multiplication, again, if A is congruent to B, then 3A will be congruent to 3B. And this is actually the heart of most of the usefulness of modular arithmetic, is that it plays nicely with both addition and multiplication. where it doesn't go so well, perhaps, or at least so cleanly, is in division. So if I had an equation like 2x is congruent to 6, I might expect by the normal rules of algebra that I should be able to divide both sides by 2 and conclude that x is congruent to 3. Is this okay? And the answer is a little funny. It's, well, sometimes. Because division of integers doesn't necessarily give us an integer. And this relation, equivalence, is an equivalence on integers. So it seems that, okay, having division, even if the division gives us an integer, it's not clear that these equations will hold. So I'll let you work this out yourself, but you can check that if n is equal to 7 in this case, this in fact will be true. But if n is equal to 8, this is not okay. So this will be false, and we'll see an example where that happens. So at first you look at it and it seems a little disappointing that I can't do all the usual algebra tricks that I might do when trying to solve equations. But looking a little closer and thinking hard about exactly when can I do this sort of division, right? When can I divide both sides of an equation by something and have it still be true? Well, it turns out that that's really the heart of a lot of really interesting number theory. So we'll get into this and we'll see exactly when can you do that division and actually how to do that division. So we'll do that. And then if we look, our last operation that we really need, and this one is clearly important for RSA, is to be able to look at exponents in modular arithmetic, but we can't do the following. So it might seem tempting to do this. If a is congruent to b, we might want to conclude that, say, 2 to the a should also be congruent to 2 to the b. That we should be able to, in some sense, reduce an exponent mod n to another exponent. And this is not okay. So this does not work at all. We can see a bunch of simple examples. However, we'll also see that there is a way to reduce exponents using modular arithmetic. And it's not to reduce them mod n, but we're going to reduce them modulo some other number. And that's going to actually be the key to showing the correctness of the RSA cryptosystem. So addition, multiplication, actually with those two together, you can also do subtraction. Those work in the normal way. Division has some caveats, and exponents are going to behave in a somewhat funny way, but a way that we can still use for fast computation. Probably the most important algorithm in modular arithmetic is the so-called Euclid algorithm, or Euclidean algorithm for greatest common divisors. And we're going to use an extended version of this, so the extended Euclidean algorithm. We'll talk about exactly how this algorithm works and why it works in just a second. But first, just remember, in the standard Euclidean algorithm, the process is to take a pair of numbers a and b, and you take the larger number and you replace it with a smaller number. I always think of this as removing some number of squares from this rectangle, and so what I get here is b mod a. Right, and the recursive part of this algorithm is to replace the big rectangle with this smaller rectangle, and then we repeat that process. So so the whole algorithm just relies on one main fact, which is that the GCD of a and b, let's assume a is less than or equal to b, is equal to the GCD of b mod a and A. So once you know this one fact, it actually tells you not only really what the algorithm is, it basically gives you a complete implementation just by doing it recursively. And we're going to take that recursive algorithm and extend it to give even a little bit more information. And so here is that basic algorithm. Right? It's utterly simple. There's a base case in this recursion. So if A is equal to 0, then we're just going to return B. And the reason that works is if A divides B evenly, then B mod A will be 0, and then the other number will be the GCD. Otherwise, we're going to use our one fact that we know, that B mod A and A have the same GCD. I've reduced the numbers, so I'm solving the same problem but on a smaller instance, and that's going to eventually get down to the base case. Okay, so standard kind of recursive algorithm. This is sometimes called tail recursion, where you just return whatever you got from the recursive call. And depending on how you were raised, you might think tail recursion is either the best thing or the worst thing. For instance, some languages it's encouraged, other languages like Java or Python it's discouraged. But in this case, I think using recursion for the Euclidean algorithm and the extended Euclidean algorithm are closest to that intuition for why it's correct and where it even came from. Okay, so that's the regular Euclidean algorithm. Our goal with the extended algorithm is to not just return this number G, which is the GCD of A and B, but we also want two other numbers, right? So we want G to be written as a combination of the A and B. So it's going to be S times A plus T times B. So we're going to return a G, an S, and a T. Now, it's not obvious that we should be able to have integers, like that they necessarily exist even, to have integers that you can write G, the greatest common divisor, as this integer combination of the inputs. And usually you might see a textbook would go through a process of proving that they exist and proving certain properties about them. But if we want to prove something exists, an easier thing to do sometimes is to just construct them. And that's what we're going to do. We're just going to give the algorithm, and we'll see just directly from the fact that the algorithm is correct that these numbers S and T exist, and we'll know how to compute them. And the recursive algorithm will essentially be the inductive proof that they exist. So let's try that. So here is the code. I've been hiding it. And we'll walk through it. So it has almost the same structure as the normal version. If A is equal to 0, that's our base case again. And we're going to return B, right? So nothing is going to change about the GCD computation. It's just that when we return it, the answer, we're going to give not just the GCD, but also S and T. And so if the GCD is B, well, B is 0 times A plus 1 times B. So the base case is pretty easy. All right. If we're not in that base case, then instead of just immediately returning the output of the Euclidean algorithm, we're going to store it in some local variables. So G, S, and T are going to be the result of calling this extended Euclidean algorithm on B mod A and A. And then we're going to use the answer there to return something else. And before we dig into what that is, we'll just derive what it should be and check that we did the right thing. So it's a recursive algorithm, and the way to think about recursive algorithms is that you check that the base case is right, and then you assume that it works for all smaller instances, exactly as you would do in a strong induction. And you assume that you got the right answer there, and then from that right answer you got on the smaller instance, you construct a correct answer for the current instance, so in this case A and B. So if we assume that this extended algorithm works correctly on the smaller instances, we know, first of all, we know that the GCD is right, but we also know that G is going to be S times B mod A, right, which was the first variable. or the first parameter, argument to this algorithm. Give myself a little room. Plus t times a. Okay, and our goal is to return g as a sum of something times a plus something times b. So we want to get rid of this b mod a. And the way we'll do it is to rewrite b mod a as follows. So b mod a is the remainder after I divide b by a. And that's like saying, okay, if I took b and I subtracted off b over a times a, but this is b over a, and then I rounded it down to be an integer. And so that if you multiply it back by a, well, you're going to get a multiple of a. In fact, you're going to get the largest multiple of a that's less than b. And so that difference is b mod a. And I add that to the t times a that I had before. So this can now be rearranged by taking the terms that are multiples of a and the terms multiples of b and group them. And what I'll see is this is, well, I have t times a, and I have s minus s times the floor of b over a, all times a, plus s times b. Okay, so this is just me doing basic arithmetic and algebra to rearrange these terms, and what I see is something times a plus something times b. Okay, so as long as we believe this is correct, now we have everything we need. We can actually just return these two values. So this is going to be the new s, I'll call it s prime, and this will be t prime. And you can see that actually that's precisely what we returned, right? This expression is that t minus s times b over a, right? Remember, double slash in Python is integer division, rounding down. And this is what we return for t. Okay, so that's it. In fact, just by believing this little bit of algebra, it shows that the answer we get, assuming it was correct for the smaller instance, is going to be true for a and b as well. So we got the correct g, s, and t, and the algorithm's actually not that much harder. In all these cases, I just point out, I am assuming that a is less than or equal to b. If b is smaller, you'd have to swap these two. But it's not too crazy to assume that, and that's it, right? That's the whole algorithm. And essentially, the analysis is doing this induction, where the heart of the induction is just this arithmetic. So as I mentioned, we can't always do division mod n, but sometimes we can. So let's dig into exactly when it works. So here was the example I started with, right, where I have 2x is congruent to 6, and I want to know, is it true then that x is congruent to 3? And if you, for instance, try x is congruent to 7, well, we can check when is 2x congruent to 6 mod 7. I guess x equals 3 works, and that might be the only case, because what other numbers are congruent to 6 mod 7? I guess we could go up to, well, 13. Could 13 be 2 times the number? Unlikely. 14, 20, 2 times 10. Yeah, it looks like it works. You can try it all out, but we'll prove exactly how and why this works for x equals 7. But we can check if x is, well, actually, I'm sorry, this is not x, this should be n. Sorry about that. This should be, if n is equal to 7, this works. And if n is equal to 8, then it's easy to come up with examples where this goes like horribly wrong, right? So I'll take x equal to, let's see, how about x equal 4. Right, so if x equals 4, 2 times 4, oh, that's not a problem. How about x equals 7? So if x equals 7, 2x is equal to 14, that's congruent to 6, but x is not congruent to 3. Right, so I couldn't do the division in this case. So this one was okay, this one was not okay. All right, so the theorem that I've written on the slide here is exactly the tool we're going to need in order to do division. And at first it doesn't look like division at all. It looks like just more multiplication, but maybe that's the point. So if a and n are co-prime, n is still going to be our modulus, there exists some other number s such that s times a is congruent to 1 mod n. Now, the reason this number s allows us to do division by a is that multiplying by s is going to have the same effect as dividing by a. So why is that true? Let's just look here. So saying that a and n are co-prime is the same as saying that their GCD is 1. And so by the Euclidean algorithm, the extended Euclidean algorithm, we know we have numbers s and t such that SA plus Tn is equal to that GCD, which is just 1. Okay, oh, I say equal to, but if it's equal to, then it's certainly also congruent to mod n. And now what is n mod n? That's 0. So this term will cancel out. That's just adding 0. And I got exactly what I wanted, which was SA congruent to 1 mod n. All right, so again, why does this help? How does this allow us to do something like division? Well, if I had ax was congruent to 3 times a, then in order to divide both sides by a, to cancel out the a's, instead of doing that, I just multiply both sides by s, because multiplication plays nicely with modular arithmetic. So s times ax will be congruent to 3 times SA. That's me just multiplying both sides by s, and now because SA is congruent to 1, I can reduce this down to x being congruent to 3. So anytime you have a number that's co-prime to the modulus, that is, if it's GCD with the modulus is 1, then you can find this other number. In fact, we already have the algorithm to find it. It's just the extended Euclidean algorithm will tell us this other number s, which serves as the multiplicative inverse of a. Right? And that's going to allow us to do division. And again, division by a will just be multiplication by s. Let's see an interesting case where this can be put to use. So let's pick our a and n to be co-prime. And I'm going to define a function, f. It's going to work on the numbers from 0 to n minus 1. And the way it works is f of b is just defined to be a times b mod n. Let's write out some values of this. So maybe we'll pick a particular example like n equals 8 and a equals 3. I think that's a nice example. Let's do that. So if these are the values of b that we're looking at, f of b is going to be 3b mod 8. So 0 times 3 is 0, 1 times 3 is 3, 2 times 3 is 6, 3 times 3 is 9, which is 1 mod 8, 4 times 3 is 12, which is 4 mod 8, 5 times 3 is 15, mod 8 is 7, 6 times 3 is 18, mod 8 is 2, and 7 times 3 is 21, mod 8 is 5. Okay, so one thing you might notice here, which is useful, is that all the numbers that we gave on the input also appeared in the output. We just reordered them, right? So it goes 0, 1, 2 to 3 to 4 to 5. They're just really jumbled up to 6, and then let's see if I can make this make sense. There we go, 7. All right, so it's scrambled the numbers up, but they all appeared. So we got a permutation. Another name for a permutation of the numbers of this form is that it's, well, this is a bijection. And is that always going to be true? And the answer is, well, yes. And the reason we can just derive this directly from the rules about division. Now that we know that a and n were co-prime, we know first that, well, if b1, or sorry, if f of b1 is equal to f of b2 for two values of b, then, well, it must be the case that 3b1 is congruent to 3b2 mod 8. And if 3 and 8 are co-prime, which they are, I can do this division. So b1 is congruent to b2. Now there would be nothing different about any of this if I replaced the 3 with any a co-prime to 8, and actually if I pick 8 to be any n. Right, so this same argument applies. So this gives us the fact that f is injective, or 1-to-1. Right, this is the definition of what it means to be injective. If you apply the function to different values, you get different values. Or the only way to get the same value is to start with the same value. All right, so that's injectivity. And if you have an injective function on a finite set like this, it's also going to be bijective. All right, we'll use this in just a minute. So we're ready to move on to exponents and show how to reduce exponents in modular arithmetic. And one of the main tools we're going to use is something called Fermat's little theorem. Eventually, we'll also see a generalization of this. Here's how it goes. Before I tell you exactly what the theorem is, we're going to kind of explore a little bit and maybe see how we might invent it. So I have these numbers 3 and 10, and they're equivalent mod 7. So I might hope that, say, maybe I can use this equivalence for exponents, right? Is 2 cubed congruent to 2 mod 10? And the answer is actually no. So let's check what these actually are. I'll do them on 2 different lines. Right, so 2 cubed is 8, which is just 1 mod 7. And 2 to the 10th is 1024, but actually I can write it in terms of 2 cubed. It wouldn't be too crazy to write 2 cubed times 2 cubed times 2 cubed times 2, because there's one more. And I already know that 2 cubed is congruent to 1 mod 7, so this is like 1 times 1 times 1 times 2. The whole thing comes out to be just 2 mod 7. So, so they're not equal. They're not equivalent. It seems to be a problem, but there's a couple pieces of information that we can glean from this. One is that, okay, yes, first of all, you can't just reduce mod n, but the second thing is that it did seem to be useful to find the exponents where if you raise the base to that exponent, mod n, you get 1, because it allows you to do all kinds of cancellation. So we're going to look for those kinds of values. In this case, one way to see this is it looks like we just reduced the 10 mod 3, right? Because it was 3 times something, and every one of those copies of 3 gave us a term that was 2 to the 3, which was congruent to 1, and it just canceled. And so it might look like 3 might be a good number. Maybe I can reduce exponents mod 3. A little bit of exploration beyond this will show that's not going to be good enough either. For example, 3 cubed. 3 cubed is 27. 27 is 1 less than 28, which is a multiple of 7. So I could you could write this as 6 mod 7, but you can also think of it as minus 1 mod 7. This is also correct. And so 3 to the 10th, I can do this same game. It's 3 cubed times 3 cubed times 3 cubed times 3. So this is equal to -1 times -1 times -1 times 3, which will be -3, or if you like, you can think of this as 4 mod 7. So in this case, I didn't get, I wasn't able to just reduce 10 mod 3, because that would give me 3 and not 4. So 3 is not the magic number for 7. We're going to see that it turns out the right number for 7 is 6. And why that's the case is pretty cool. Okay, so here is Fermat's little theorem. It's called his little theorem because it's, in fact, the most important thing he ever proved. But there's another important result that has his name on it that was maybe a little bit more famous for being hard. That's sometimes called Fermat's last theorem, which unfortunately has the same acronym. I apologize for that. But here's the statement. If we have a prime number p, then for all numbers a, all natural numbers a, the following is true. Right? A to the p is congruent to a mod p. All right, so I can give you a simple proof of this. One way to do it, because as you see, it's a universal statement about all natural numbers, so induction is a natural place to start. So the proof will be induction on a. The base case is just checking a equals 0, and 0 to the p is congruent to 0, because it's equal to 0, mod p. And now we're going to do the induction, so we need to show that a to the p congruent to a implies that a plus 1 to the p is congruent to a plus 1. Right? So that's our goal. So this is our inductive hypothesis, that a to the p is congruent to a, and we just want to conclude this. And the way we'll do it is to use a nice little power tool, which is the binomial theorem, which we've covered. So a plus 1 to the p by the binomial theorem, remember it breaks it up, so it's going to be p choose 0 times a to the 0 plus p choose 1 times a to 1 plus etc. all the way to p choose p minus 1 times a to the p minus 1 plus p choose p times a to the p. Okay, so this is the expansion. At first it doesn't look too helpful, but a couple things will jump out at us. P choose 0 is 1, and a to the 0 is also 1. So this is all 1. And at the end here, p choose p is also 1. So this is just a to the p. And every term in the middle has a coefficient that looks like p choose k for some k between 0 and p. And when you expand that out using the definition, the numerator will have a p factorial, and the denominator has to cancel everything in the has to cancel out in order to get us an integer. But nothing in the denominator is going to cancel the p in the p factorial. So all of these coefficients are going to be multiples of p, and if it's a multiple of p, that means it's congruent to 0 mod p. So these are all going to be congruent to 0 times a to the 1, etc., 0a to the p minus 1. And so all of these terms will cancel. And the result in the end is that this is so congruent to 1 plus a to the p, but by induction, that a to the p is congruent to just a. Okay, and this is exactly the thing we were trying to prove. Right, so let me just write it in the other order just to get the pattern right. So this is a plus 1 to the p is congruent to a plus 1, and that's the induction, and so it's true for all a. I'll give you just a moment to look at this, let it sink in. That's really the whole argument. And you may see another equivalent version of this theorem. So this first thing is what we proved, right, is that for all a to the p is congruent to a. But one thing you often see is it written a little differently, which is that for all a, if a and p are co-prime, then a to the p minus 1 is congruent to 1 mod p. All right, so there's a couple things. We can see that this expression, if a and p are co-prime, I can divide both sides by a, and this is exactly what I get. So this is our division rule played out in this way. And it seems like exactly the kind of thing we wanted, right? We found an exponent, p minus 1, such that if you raise a to the p minus 1, you get 1. So that's going to help us a lot when doing cancellation. And in fact, it's going to give us a really nice corollary to the Fermat theorem, which is that if b is congruent to c, modulo p minus 1, then, all right, for all a co-prime to n, oh, sorry, not n, I want p here. Yeah, for all a co-prime to p, we can write the following. We can say that a to the b is going to be congruent to a to the c mod p. Right? So if we were doing mod p arithmetic, we can reduce exponents mod p minus 1. Again, this is assuming p is prime. And the proof of this corollary just takes one line here. We just take a to the b, and if b is congruent to c, that means that b is equal to c plus some multiple of p minus 1. So this is equal to c plus some quotient times p minus 1. And just using our basic rules of arithmetic with exponents, we can rewrite this as a to the c times a to the p minus 1 raised to the q. And since Fermat's theorem tells us that this a to the p minus 1 is congruent to 1, the whole thing is a to the c times 1 to the q, which is just a to the c. Again, this is all mod p, right? So we reduce the exponent mod p minus 1, and we get a result mod p. Fermat's theorem told us how to do reduction of exponents in modular arithmetic when the power was, when the modulus was a prime. If you want to have a modulus that's not a prime, which actually is going to be important for RSA, we're going to use a more general theorem called Euler's Totient theorem. So this is going to go just beyond Fermat's theorem. So here's the setup. I'm going to fix a number n, and I'm going to define this set S. And S is going to be all the numbers from 0 to n minus 1 that are co-prime to n. So anything that doesn't have any common factors with n other than 1. So then I'm going to define this number phi. So phi for n is equal to the size of S. So it's the number of numbers less than n, natural numbers less than n, that are co-prime to n. And the theorem that we'll prove is that if a and n are co-prime, then a raised to the phi of n will be congruent to 1 mod n. All right, so this is going to, again, give us some exponent that we can raise a number to get 1. And that's going to help us with cancellation and reduction of exponents. All right, so I'm going to give you a complete proof of this. At first, it's going to seem a little strange. I'm going to just define some other set, T, and I'm going to build it from S. So what I'll do is I'll take every element S in S, and I'm going to multiply it by A and take it mod n. Okay, this is a function we've seen. This is the one we used previously to permute the numbers from 0 to n minus 1. And, but now I'm only taking those numbers s that are coprime to n. All right, so we saw already that this function, when a is coprime to n, this function is injective. So for every element of s, we're going to get a new or distinct element in t. And so, in fact, that means that the size of t will be equal to the size of s. And, well, we have a and s or a and n are coprime. And s and n are coprime, because that's how we define the set S, the big S. And so the product of these will also be coprime. So AS is going to be coprime to n, and maybe I'll write it like this. We have the GCD 1 is equal to the GCD of AS and n. And by just one step of the Euclidean algorithm, that also implies that this is equal to the GCD of AS mod n and n. And that is another way of saying, right, this whole thing just evaluated to 1, and therefore AS mod n and n are also coprime, which means that all of the elements of T are also coprime to n. But that was the defining property of S. So what we actually just concluded here is that T has to be exactly equal to S. These are the same set. All right. So if they're the same set, then when I take the product of all the elements in S, that's equal to the product of all the elements in T. But the elements in T, by definition, are just taking the elements of S, multiplying them by A, and reducing them mod n. So this product right here will be congruent mod n to just the product of A times S. Now, I can rearrange this product because multiplication is commutative and associative, and I can get that this whole thing will be A raised to some power, right? How many copies of A do I have? Well, 1 for every element of S. Number of elements of S is exactly phi to the n, 5n. And then the remaining part of this product is just the product of all the elements of S. Now, I would like usually to just cancel this out, which would be like dividing both sides of this congruence by all the multiples of, or by all the elements of S. But I know I can't always do that, right? I can only do that if I'm dividing both sides by something coprime to n. But the good news is that's exactly how we define the set S. So every element S in here can be canceled. And so the result is just exactly the theorem statement, which is that a to the 5n is congruent to 1 just by dividing both sides by all the elements of S. So that's the theorem. This is called Euler's Totient theorem. This 5n is called the totient function. Let's see how it helps, right? So this is going to give us another way to reduce exponents. Right? So if b is congruent to c modulo phi of n, and again, a and n have to be coprime, then a to the b is congruent to a to the c mod n. You can think of this equivalently. It's like saying that a to the b will be congruent to a to the b mod 5n mod n. So this is how we, again, reduce exponents in modular arithmetic. And let's check, is this true? What will be a proof of this? It's actually the same proof we used when doing the Fermat's little theorem. B was congruent to C modulo phi of n. So A to the B was equal to A to the Q phi of n plus c, which is equal to a to the c times a to the 5n to the q, which is a to the c times 1 to the q, just a to the c. Okay, so the proof is basically the same as we saw for Fermat's theorem. In fact, this is, right, Euler's Totient theorem really is just a generalization of Fermat's theorem. Fermat's theorem can be seen as a special case. Let's prove that, right? So just check that if p was prime, then phi of p is going to be equal to p minus 1. And that's easy to check that if I look at numbers less than p, natural numbers less than p, they're all co-prime to p because p is prime, except for 0. So just 1 up through p minus 1, those will be the numbers that are co-prime to p, and there's exactly p minus 1 of them. So if I plug in p minus 1 for, into the Totient theorem, that's exactly Fermat's theorem. Now the case we're interested in for RSA is going to be the case where n, the modulus, is the product of two distinct primes. So we have p and q, and n is just equal to their product. So in this case, phi of n is equal to p minus 1 times q minus 1. All right, how do we prove that fact? Well, we're looking for all the numbers co-prime to n. Instead, what we might do is do counting by complement. Right? So counting by complement would say, well, we take all the numbers, there are n of them, from 0 to n minus 1, and we subtract out those that have some common divisor greater than 1 with n. So this means we're just going to be subtracting off, well, there's the multiples of p and the multiples of q. And if you remember the inclusion-exclusion principle, we have to be careful when doing this kind of sum that we also subtract off the intersection. So we have to subtract off the multiples of both. And for numbers less than n, the only number that's a multiple of both p and q is going to be 0. So there's just going to be one possibility there. So n was equal to pq. We subtract off the multiples of p. How many are there less than n? Well, let's see. There's 0, p, 2p, 3p, 4p. We go up to, but not including p times q, right? So we only get 0 times p all the way up to q minus 1 times p. And so that's q different multiples of p. By the same argument, there's going to be p multiples of q. And the minus is plus, so plus 1 here. And that's exactly p minus 1 times q minus 1. Okay, so that's just a quick check. It allows us to bring in some of our tools of counting, right? We did counting by complement, inclusion-exclusion principle, and we get exactly this value. So if I have a number n that's a multiple of 2 primes, then I know exactly what phi of n is. All right, so that I know how to reduce exponents when doing mod n arithmetic. So we're ready to get back to RSA, and now we can actually know enough modular arithmetic facts to actually show that when you encode a message in RSA and then you decode it with the private key, you get back to the original message. Let's see how this works. So remember, we have E and N are the public key, and we've kept this number D private. And so we chose N. N is going to be a product of 2 primes, P and Q. The property we want is that E and D are going to be inverses mod phi of n. So, if we picked E, we know how to get D by the extended Euclid algorithm, and we know that something about this probably is going to mean that we can reduce an exponent. We can see exactly how that happens. So to encode a message, right? I've got my ciphertext. It's going to be, if you remember the definition was, we take the message, we raise it to the eth power, and we reduce it mod n. So if that's the case, this is another way of writing that C is congruent to m to the e mod n. Okay, so that's our ciphertext. Now if I decode it, what I do is I take C and I raise it to the dth power. So that will be congruent to m to the ed mod n, right? So there's no problem with raising both sides of a congruence to some power. But now we know exactly what to do, right? Because I have an exponent mod n, and I have that exponent is congruent to something else mod phi of n. So I can use this theorem we just proved, and I get that c to the d is congruent to m to the 1, or just m mod n, and that gets us that c to the d mod n is in fact equal to m. All right, so that's our decoded message. And that's it, right? So that's why the RSA cryptosystem works in terms of giving you back the original message. It's why you can decode, and it also gives you some hints on how to actually do it, right? So if you want to actually construct these keys, like how do you generate the keys? Well, simple process, right? We pick those two large primes, P and Q, right? So we will set n to be equal to their product. Let me get my face out of the way. And how do we do it? Well, it turns out that to find large prime numbers, you just pick random numbers and then you check. And it turns out it's easier to check if a number is prime than it is to actually factor it. So you don't find the factors, you just check to see if it's prime by checking to see if it has a bunch of properties that prime numbers have that are maybe more rare for non-prime numbers. So we saw one property, which was Fermat's little theorem. Fermat's little theorem isn't quite enough. There's a more general algorithm for checking primality quickly by randomness. It's called the Miller-Rabin test. Incidentally, this is named after Gary Miller, who was my PhD advisor. Once you have your two large primes, since you know what they are, you know what phi of p is, or phi of n is, and that's going to be p minus 1 times q minus 1. So you're going to choose a number e. This is part of your public key, and it has to be co-prime to phi. And the reason for that, of course, is so that there exists an inverse d. And again, if you want to do this, you can just guess a number by randomness and then check if it's coprime. And the way you would check it is, well, you would just run Euclid's algorithm. And if you're going to run Euclid's algorithm to check if it's coprime to phi, you might as well run the extended version. And when you run the extended version, you get d, right? So you end up with e times d is congruent to 1 mod phi. Okay, so all of these are algorithms that, other than the primality test, all of these are pretty straightforward, right? These are algorithms we know. We know that to do the encoding and decoding, you have to use our fast modular exponentiation algorithm by repeated squaring, and to compute the private key from the public key, you use the extended Euclidean algorithm. Okay, but if we're going to see why this seems to be secure, we can actually try to break it. And breaking it wouldn't be too hard, assuming one thing. So let's just pretend that we know how to do one little task, which is that we can factor integers. So someone gives me an integer, and I can factor it into two other numbers. If I have this program and I know this public key, right, because everyone knows this public key, it's published, say, on the internet, then I can use this factoring algorithm to produce PQ. And so if I know P and Q, I know that phi of n is equal to p minus 1 times q minus 1. So I can play the same game that whoever generated the keys played, which means I can just run the extended Euclidean algorithm on the public key and phi, and I will get d. Because remember, the output of this algorithm will be numbers, right? It'll be, well, the GCD of these two numbers is 1, right? So 1, and I'll get a number, what, s times e plus t times p minus 1, q minus 1. And so modulo this number, right, this is, again, phi. So mod phi, this is going to be congruent to, this means I have SE congruent to 1 mod phi, and so actually S is equal to the secret key. All right, so just running the extended Euclidean algorithm will extract the secret key, assuming that I can factor this number. So the corollary to this is that it seems like factoring is hard, right? The fact that RSA has not been broken on a large scale seems to indicate that factoring is also a computationally hard problem. It doesn't seem like if I give you numbers with thousands of bits that you can find its factorization in a reasonable amount of time. It seems like all the known algorithms take an amount of time which is exponential in the number of bits. Okay, so this is also why there is some extra hype around quantum computing, because it's known that for quantum computers there do exist algorithms that can factor integers, and it seems to be a reasonable amount of operations. But as of right now, there don't exist quantum computers at the scale that can factor, say, the keys for cryptography. Okay, so let's just overview. What did we talk about? Remember, we're doing public key cryptography, and we can encode messages just using exponentiation and modular arithmetic, which again is based on a fast modular exponentiation algorithm. So we can encode this way, we can decode this way. There's this nice symmetry between encoding and decoding. Right? The key to making this work is we had to understand about how to do division mod n. Right? You can only divide by those numbers that are co-prime to n, because they have some other number that you can multiply. That is, that number is going to be the multiplicative inverse. And we also looked at reducing exponents mod n. And we have two tools for this. For prime moduli, we had Fermat's little theorem, and more generally, we had Euler's Totient theorem. Okay, and so when we put this all together, we got RSA, and we saw that encoding and decoding actually work, and we also saw that how you could break this with factoring. So if you could factor integers, then you could break RSA. Okay, so that's an overview covering pretty much all of the math needed to understand RSA. I guess the one thing we left out was that primality test, but I encourage you to look it up on your own.